Welcome everybody, good morning, and welcome to this session. And my name is Nikita Ivanov. I'm founder of a company called GridGain Systems, and I'm also on a Apache Ignite PMC. So what I'll try to talk about in the next 30-35 minutes is talk about some of the pretty cool integration we have in Apache Ignite with Apache Spark. And it's based on the shared in-memory RDD idea. So as probably most of you know, some of the basics with Spark. Spark really doesn't have a kind of long-term storage functionality. It's a system where you can load data into it like a data frame, and you work with the data frame, and once you actually stop working with the data frame, it kind of disappears. You have to drop it. So that's not a deficiency, it's by design. That's what the Spark is. It's a processing system, right? And it's one of the kind of, when people started to play with Spark a number of years ago, it didn't really, cause any problems, because that's exactly how Spark was used. You load some data into it, you work with it, you drop it. As we get progressively more sophisticated with the Spark usage, we start to have a Spark pipelines where you have many, not many, but multiple Spark jobs in succession. And there the problem could be pretty significant, because once one job in Spark finishes, you have to store the intermediate results somewhere. And we've been dropping them on HDFS, on Tachyon, on a variety of different file systems, and typically those are disk-based, and therefore you have this massive performance differences, right? Your Spark jobs runs in memory, but then you have to drop results somewhere on the disk, and the next job you have to pick it up from disk, read it back, and use it again. So a lot of our customers and users basically indicated this problem, and about a year ago we developed what we called in-memory SharedRDD, which is essentially a standard RDD in a Spark speak that is backed by technology that's available in Ignite. So that's what I basically want to talk to you about today. So what we're going to do, we're going to talk about what is Spark very briefly. It's not a presentation about what is Ignite. It's not a presentation about Ignite, but we'll talk about some of the basics and some of the key technology like in-memory compute grid and data grid that is behind the implementation of our in-memory RDD. We also talk about some of the key benefits when you actually start using the Ignite-backed RDD. Your SQL becomes dramatically faster than it's available on Spark natively. So we'll basically, I'll talk about a lot about SQL and what's available there. In the end, I'll show you a quick demo. We're going to run Spark and Ignite through Zeppelin. Zeppelin is a great Apache project, gives you this kind of notebook interface. And I'll show you the differences in SQL performance when you run on a Spark RDD or whether you're running on SharedRDD backed by Ignite. You're going to see the difference in that particular implementation of that particular performance. So it's going to be fun. Stick around. So project history. How many of you guys actually know what Apache Ignite is? Just raise your hand. All right, quite a few. All right, so very quickly, Dimitri and I started working on the GridGain project literally almost 11 years ago. In 25, we wrote the first line of code. And the rest is history. So in 27, there was the first public release. In 29, we have our largest production customer with over 2,000 nodes. So roughly about 7 years ago, we were running on 2,000 nodes already. It's a pretty significant deal, by the way. There's not that many projects that can say that. I mean, I would say probably Cassandra and Hadoop are about the only two other projects that really can enjoy that large deployments and be successful. So 2010 from the company around 2011. Every 10 seconds around the globe, somebody starts GridGain. In 2014, the same code base migrated over to Apache Software Foundation. It became Ignite. We had to change the name because of the legality. So Ignite essentially is a very old in production level or production quality code base. So although it's kind of a newer version, literally right now I think it's 1.6 just about to be released. It's pretty much a decade old production quality code base that's been around for a while. And in 2015, we got top level project. By the way, one of the fastest graduation, I think, behind Spark and Hadoop. So that's the history of a project. So what is Ignite? Again, I'll be very quick. It's not a presentation about Ignite specifically, but we call it Ignite as a memory data fabric. And essentially, it's a piece of software. It's a Java-based or JVM-based software. Portion is written in Java, portion written in Scala. That essentially slides architecturally in between your data sources on the bottom and your applications on top. And allows you to move data away from flash and disk storage into the RAM level across multiple computers. And once data is in there, things go really, really fast. The two key words about Apache Qunari is speed and scalability. That's what it's all about. We deliver speed and scalability. We deliver speed by actually moving data away from slow disk and flash, from those slow block-level devices, into the byte-addressable RAM across many, many computers. That's your speed. Scalability comes from a massive parallelization. Surprisingly enough, a lot of folks who basically come to in-memory computing, in the first time, they don't realize that in-memory computing is almost synonymous with the distributed processing. And the reason for this is kind of a necessity, historical necessity. 10, 20 years ago, there was absolutely no way to do anything in a single computer. The RAM was not big enough. So we had to string together dozens and dozens and dozens of nodes in a cluster to really do anything useful. So today, many in-memory systems, if not all, are one of the most sophisticated distributed systems in existence because of necessity. We had to do a lot of cluster computing, a lot of distributed things to really actually have the system that works. It's not the same for memory databases, by the way. If you look at MemSQL, VolDB, or HANA, or anything else, they don't have the same kind of historical background. They don't have to be highly distributed systems. It's a bad and good in both ways. In-memory data grids, and we're based on that, historically had to be. They had to be distributed system, and that's why the scalability is the prime benefit we can deliver. And we routinely run on hundreds and hundreds of nodes in a full transactional topology in production environment for years without downtime. It's a big, big deal. So anyway, Apache Qunari is all about two major benefits. Speed, we're running everything on the speed of RAM. It's a byte-addressable RAM speed. And scalability by massively parallelizing our processing. So on the bottom again, we slide in between our data source and applications. On the bottom, you can have anything. We work practically with any data source in the back end, or not at all. One of the cool features about the Apache Qunari, it can and often does serve as the system of records. We don't have to have a backend store at all. You can have it as an option. You don't have to. But we can work with SQL, right, of NoSQL databases and Hadoop or straight file systems. And on the top, you basically have a variety of different clients. We have Java clients, .NET clients, C++ clients. We have full SQL support. So basically, anything your applications talk to, they can talk the same way to the fabric. And the reason we call it a fabric is because of this. From the beginning of our project, we thought that in-memory computing is not just a single trig point. It's not just a single key value store. It's not just a processing engine. It's an idea of keeping data in a partitioned way in memory. And then once you have that data, you can have all the different type of processing on this data, right? So that's what we actually developed in Apache Qunari. We call it a fabric. It's a multi-paradigm processing framework, if you will. So not only we have a data grid that gives you a SQL and a key value processing, we have a compute grid, which gives you a tremendous capability for classic HPC, MPP, and MPI, all those acronyms, if you guys are familiar with them, type of processing. So you can do very effective traditional parallel high-performance processing, anything from Monte Carlo simulation to a mathematical processing and whatnot. We have a service grid, which is basically the same SLA on the same in-memory grid. We have in-memory streaming, which is the great concept if you want to stream data into the in-memory system. We have in-memory streaming. We have Hadoop and Spark acceleration and integration. We'll talk about this today. Clustering. We have a memory file system. How cool is that? You can basically have a normal HDFS compliant file system right in memory across hundreds of computers, if you like. Some of the operations on this in-memory file system over 1,000 times faster. Think about this, 3 orders of magnitude faster than, for example, HDFS. Again, not because we're smart, because we do it in RAM, and it's fast. Believe me, it's fast. So the big idea behind the data fabric and the word fabric is that it's not a single trig point. It's not just a key value store or a SQL or something else. It's all this and above. It gives you a very strategic view on what you can do with in-memory system. Once you have data in it, you can do quite a lot. You're not really limited by one single API. We practically cover all the bases today. So there's a two technology that's very important for a Spark integration, and we use them for this implementation. It's a compute grid and data grid, and I'll talk about them individually. So the compute grid is a very simple idea, and actually when it comes to Java space, we essentially pioneered this idea in 25. When Apache Qunari really came out as a code base in 25, we had industry-first compute grade available. So compute grade is essentially a new way of saying traditional high-performance computing. Think about this. If you have a long-running task and you have multiple computers in front of you, you can split this task into multiple subtasks, execute those subtasks on those nodes in parallel, get results back. So if you have n nodes in the classic, normalized way, you can execute this task n times faster. That's it. That's the whole idea behind a compute grid. The rest of it is a bunch of details and the whole can of worms of what we can do, how we do it, how to fail over, how to do all the different things. So we have multiple MapReduce implementations. One is Hadoop compatible, another one is our own, much more optimized, much more kind of fitting for a memory model. We have things like zero deployment, which is actually a wonderful clustering feature. If any of you guys work in a distributed environment, you know that one of the biggest pain in the ass is to deploy things, right? You have 20 nodes in front of you. You have to constantly, ship something over, start, restart things. Anybody working in a Hadoop environment know what I'm talking about, or a Globus environment, for example. We have a zero deployment. You never deploy anything in the system. Everything gets deployed completely on demand. I can have 20 nodes in Siberia right now. I can basically change a line of code here and route from here. It will automatically deploy whatever is needed. It will properly version. It will do all the magic behind the work. You just basically work as you would do locally. Very cool feature, tremendous productivity boost. So we have a cron-like task scheduling. We have a state checkpoint, but the coolest feature for anybody working, for example, in bioinformatics. Almost everything in this space takes forever, and this is one of those things that can stack checkpoint the execution of a task. If a task takes an hour to execute, imagine this, and you try and debug this. If it fails in a 45-minute, well, guess what? If you don't have this, you're out of luck. You have to restart from the beginning. With the state checkpoints, the task can restart from the latest checkpoint. For example, you can checkpoint every 5 seconds, so you're only going to lose 5 seconds of the execution. So it's a great feature. We're about the only ones having this. So we have load balancing, failover. Goes without saying. If you have a distributed systems, you have to have those features. We have fairly advanced implementation, both load balancing and automatic failover. And I'm not going to talk about SPI design, but everything we do is completely pluggable. Anything from communication to discovery, all those different components can be completely plugged in with your own implementations. Another technology that we used to implement in-memory RDDs is in-memory data grid. So, similar to in-memory compute grids, in-memory data grids really solve the problem of how do I parallelize data storage. Think about this. So the compute grid solves the problem of how do I parallelize the processing, right? I take the task, I split the task, run the task in parallel, and I get my results back. In data grids, the problem is similar, but basically defines, okay, if I have a terabyte of data and have 10 nodes in front of me, how do I store my terabyte on these 10 nodes? So typically, you have to, most of the time, you have to split this data in 10 pieces and let each of these 10 nodes keep 1/10 of the data you have. That's kind of simplistic view, but that's what data grids do. And obviously, behind that kind of simple definition lies the whole long list of capabilities and features and whatnot. So how do I transact, how do I failover, how do I do all the different things in this scenario. So that's what data grids do. Data grid is probably the biggest component we have. It is the system of records, basically, that's responsible for most of the data processing, if you will, or data storage in Ignite. That's where the SQL exists, that's where the key value store exists and whatnot. So let's go line by line here. I can quickly give you some sense of what's happening. So it is a key value store. And I've touched it yesterday on this topic in my presentation, but the key value store is extremely important. It's primitive and simple on purpose, because the key value is a fundamental data structure that gives us the ability to mold different views on the same data, right? Once you have a key value store, you can look at exactly the same data as the SQL view. You can view the same data as a file system view, or for example, from MapReduce, or from streaming concept, or anything else. So the key value is extremely important, not only because it gives you a basic key value access, but also because it's a very, malleable to whatever you want it to have, or any way you want to look at the same data. So it's based on the distributed in-memory key value store. We both support replicating and partition caches, or partition data stores, if you will. It's important feature because it gives you two kind of diametrically different models of storing data. In a partition data storage mode, every node, let's start with replicated. In replicated data mode, every node stores exactly the same data set, the entire data set. So your entire capacity is limited by capacity of a single node. On the flip side, it gives a tremendous high availability. Every node has exactly the same data size. In a partition scenario, in a partition mode, every node has only a portion of the data, right? It's back to our example. If I have a terabyte of data in 10 nodes, in a partition mode, this is exactly what's going to happen. My node will have one predominant, approximately 1/10 of the data size. Essentially, data that is optimized for capacity, naturally, it will have less high availability than the replicated mode. What's really cool about Ignite, you can mix and match these things as much as you like. You can have 20 caches in replicated mode, each configured differently. You can have 20 partition caches in exactly the same system, all configured differently, exactly how you need it. So you're not bound to one or another system. You can basically create little data stores, little data lakes for whatever you want to have. You can configure them with the two mode and then configure deeper for each of this mode individually. So definitely in-memory data grids do work best on the terabyte scale payloads. I don't think in-memory system really good for petabytes. I don't think anybody is interested in gigabytes today, so terabytes is our sweet spot. And for that we have a nice off-heap implementation. And I think anybody knows from Java space, one of the biggest problems we have today is the kind of on-heap Java management that doesn't scale beyond 10, 15, sometimes 20 gigabyte the most. If you have large blades, you have to use off-heap, so we have off-heap implementation. And the bottom line, we can use essentially the entire physical RAM on the box. So if, we recently tested it, I think I mentioned it yesterday, on the Fujitsu M10 system, which has up to 64 terabyte of RAM. Think about this, 64 terabyte of RAM on a single computer. And it worked beautifully, and it's a wonderful system. It's actually, I think it's a new renaissance on the verticalized, scaled up systems as we know them. It's a Lattice box, literally with up to 64 terabyte of RAM, full addressable DRAM, 64 terabyte. I always keep saying that 5 years ago that would be the data center, and today it's a single computer. Pretty cool. So we have a high available in-memory replicas. This is basically our way of saying that even though we partition data in partition mode, some of the nodes can have replicas to really gain more of a high availability. So you can lose in the capacity, but you gain in high availability. So in the partition mode, you can really configure your system for whatever mix you want to have. If you have 0 replicas, well, you're not very safe because the computer goes down, you lose the data, and you don't have much of high availability. If you have 2 or 3 or 4 replicas, you're going to lose on the capacity of a cluster, but now you're getting a lot of durability, and you're getting a lot of high availability. That's why those are pretty cool. So we have automatic failover, it goes without saying. We also have, probably the most important point here is distributed asset transaction in SQL. Actually going to have I think the whole slide in SQL later on, but distributed asset transaction is a pretty cool deal again. It doesn't really affect as much RDD implementation. We didn't really use that, but it's a cool thing to mention. So we have probably one of the best implementation for transactions in a memory data grids, bar none. We have both optimistic and pessimistic transactions. They're fully based on a two-phase commit protocol. We're very proud of this. We also have a lot of configuration to relax consistency to gain back the performance from two-phase commit protocol, so you can be just as fast as eventually consistent systems, but you don't lose the capability to be fully consistent as you would in normal transactions. So that's a very good deal. I think it's a very fine and very well thought out implementation that we have. So we also have a SQL in-memory data grid. Remember this, we have key value in a SQL and have many things. That's the beauty of the key value store. We can mold the same data as a key value or as a SQL store. Exactly the same data. As a matter of fact, in our system, you can write the file through file system API, read it from key value, or read it from a SQL store. So essentially, it's a pretty cool system. You can write the file, then read the same file through a SQL select statement, for example. It's the same data, you just have a different access to it, different access pattern to it. So, based on these two technologies, that's what we developed. Essentially, when we looked at the problem with a Spark RDDs, how do we can solve this? There are two kind of obvious ways to solve that. One is to basically use our in-memory file system, right? And if you're already using some kind of in-memory file storage for storing results between Spark jobs, that's the easiest way to go, right? You have an in-memory file system, just basically switch to different essentially URL in the file system and just start storing this in memory. But basically, it doesn't really give you much because it just basically it gives you a sync with a slightly better speed. Not slightly, but better speed. The better application or better way to do that, although it may require extra few lines of code of change, is what we call SharedRDD. You can literally pipe your Spark RDD into this RDD. This is normal Spark RDD. Think about this. It's exactly the same RDD that you guys have been using in Spark forever. It's only backed by Ignite implementation on the back end of it. So it's going to stay in RAM. It's going to be distributed across all the nodes if need to be. And you can use exactly the same RDD to read data from as your next pipeline job in Spark without losing a single bit of performance. It's right there in the same RAM space where you're running the rest of your Spark pipelines. So in-memory SharedRDD is probably the best way to integrate or integrates Ignite Spark, will basically just gain a storage capability, a long-term storage capability for Spark pipelines. This is the best way. And there's really nothing to basically even show you guys on the code level. If you guys work with RDD, you just work with RDDs. There's literally as simple as this. There's no API, there's no changes, there's nothing else. It's just a different RDD style, type. But from an API standpoint, it's exactly the same RDD that you have already. And a good example, and I'm going to show you the demo with a Zeppelin integration. Zeppelin doesn't even know it's working with something else. It's working with RDD, as a matter of fact. So let me talk about a SQL, because I'm going to show you a pretty short demo of what kind of performance differences you gain when you work with a Ignite-backed RDDs and running SQL on them. But we have probably one of the best SQL implementation across data grades. About the only systems that would have better SQL implementation would be traditional databases. We're probably not going to compete with HANA or VaultDB and MemSQL on a SQL compliance. That's kind of not our goal, but across a non-database and memory systems, we probably have the best SQL implementation. So first of all, we ANSI 99 SQL compliant. We use H2 local engine. That's a very important decision we made a long time ago as far as Ignite implementation. So instead of writing our own SQL parse and optimizer and doing the whole rigmarole of things that Oracle and all this world spent decades to do, we actually choose to use a high-performance H2 local engine on each node. And only what we do, we provide a distribution across the cluster. So we read the SQL, we understand how to distribute processing of that SQL particularly. We ship out the executions to different nodes, but locally in each node, the H2 picks up the load and does the whole SQL execution on each node. It's a wonderful design. I think we just basically really struck the goal when we decided to do so, because everybody else in the industry is struggling with rewriting the SQL optimizers and doing SQL parsing and everything else. We actually rely on a system like H2 that's been in development for years and years. It's one of the best local SQL engines. So we're shipping with GDBC driver. We also think about to ship ODBC driver. So you can literally just essentially connect to Ignite through an absolutely standard means of connecting to Ignite, like GDBC driver, for example. Topology change tolerance, pretty big deal, by the way. In the large clusters, you constantly have something up and down, and especially when we're talking about hundreds of nodes, on a daily basis, you're going to have nodes up and down coming up in the cluster. So your execution has to be topology change tolerant, and we have that as well. So you can be safe when you're querying data, you're querying the actual, you're not going to have any losses because some of the nodes up and down. So it's basically transactional processing here. Not in the sense of data transactions, but more topology transactions in a way. So we have in-memory indices, and we actually do have indices, unlike Spark SQL, for example. We actually do have pretty advanced indices. We can both keep them on heap and off heap. We support things like distributed group by aggregations and sorting naturally. You can run normal SQL, and we're going to take care of distribution. We have cross-cache joins and everything else. We have ad hoc SQL support, by the way. So you don't have to, like in many of our in-memory databases, you don't have to know your queries up front. You can essentially just write them there like in a Zeppelin or in a code. You don't have to know all the queries up front. You basically have a complete ad hoc capability from a client perspective, from a programming perspective. One of the coolest features we have a custom SQL functions you can write in any JVM language, Scala, Java, Clojure, whatever you like. Think about this. This is as close as you get to have a normal store procedures in SQL. You can literally write a function, any functions you like, in a normal language like Java, and use that function right in the SQL processing. It's pretty cool stuff. SQL is pretty limited, right, for a lot of things we do. But you can really augment this by writing, again, any function and really plug it in SQL. It's very simple. We have a bunch of examples for this. This is the coolest feature. It's probably used by almost every project we're seeing because it's such a convenient thing, right? You can have a SQL which is basically index-based access, and you can still have your own functions written in an extremely simple way in the same language you're writing every day, like Scala and Java and whatnot. So we have things like automatic GUI-based schema import. So if you have an existing database, we can import into the RAM pretty quickly. We do support schema changes, dynamic schema changes if you use our binary objects. We support geospatial indices as well. We do support the syntax queries. Again, it's not SQL, but it's kind of in the same querying capability. And we're coming up with quite a few interesting things in the community, things like a disk-based support and uncollocated join support. But anyways, just a basic quick overview of what we do on the SQL side. This is a pretty cool example of how that actually looks in I think it's a Java code, right? I don't do Java for many years from the Scala, so I'm not really recognizing this. It's actually the Java code. So very simple. Again, it's straight out SQL. You can basically see I think it's a join here. It's another example. It's a very simple. Again, it's a group by example. Again, it's a very standard SQL. There's nothing there is specific. There is no kind of bastardization. There is no dialects, special keywords. If you know SQL, you can use SQL with us. As simple as this. There's no limitation. It just works. So what I'm going to do in the next 10 minutes, if not less, let me show you a demo. So it's a pretty cool demo. How many of you guys are familiar with a project Zeppelin from Apache? Excellent. So Zeppelin essentially is a notebook interface, right? It's a very popular concept. It gives you literally a kind of notebook view on the data. What we're going to do essentially is I'm a Zeppelin configured with two data sources. One is Spark. It runs on one node, and one is Ignite. It runs on one node again. I loaded up exactly the same data set in both. I'll actually show you what the data set is. And we're going to run some queries, and we're going to see some performance differences. So bear with me. Let me just cancel out from here. So let me show you what we have. So over here, I basically started the master and the worker node for Spark, and then we can go to Spark here. And by the way, let me just go back here for 1 second. If you look at this URL on the bottom of this slide, you can basically run exactly the same demo yourself. It's all open source. If you look at this GitHub page, it'll give you all the instructions how to run this demo. So there's no gimmicks. You guys can do it entirely yourself. The entire code base is free and open source. So this is the master for Spark. It has a one worker node, right? It's right here. And when it comes to Ignite, I just ran the Ignite right from the idea. It's right here. We're running Ignite 1.5. By the time of the end of this week, probably going to have 1.6 ready out. So it's a one node. And as far as the data set, essentially here's a data set. It's a pretty simple data set. If you just, I can show you right here. It's two JSON files. It's essentially organization JSON and the person JSON. Very simple structure. And I think it's somewhere right here. I can basically give it to you. Just 1 second, I'll show you the file itself that generates this so you guys would know. Yeah, it's right here. So essentially, we have 500 organizations and 1,000 people per organization. That's the entire data set. It's not big enough, but it's good enough for kind of demonstrating that. So we're generating a bunch of two JSON files, and we load these two JSON files into the both systems. So let me show you how. And this is, by the way, this is Zeppelin interface. It has now integration with Apache Ignite and Spark, by the way. I think somebody contributed to Apache Ignite, Zeppelin integration, so we do have integration with, well, Zeppelin has integration with Apache Ignite. So if you look over here, there's integration with Ignite right here already in Zeppelin, and there's definitely integration for Spark. So there's two notebooks here. Let's just go in the Spark demo notebook. So basically what we've done, and I already done, so I don't want to waste your time here, but basically I've loaded up this this organization JSON file, created a data frame for it, and I also loaded the person's JSON file, created data frame for it, and we registered some temp tables, right? So organization temp table and the person temp table. And we can run basically a bunch of queries now. Now we have this little structure, right? Again, very, very simple organization persons, right? Very simple. We can run a pretty interesting query. For example, I'll just clear out this output here, and let's learn this example. What it does essentially, it gives you the person and the organization average salary for that organization. So we can run this query. It takes about, I already tried this morning, it takes about 15 seconds, give or take. So that's actually a real life querying capability for Spark. It does the querying right now. So we get results back, and we can see that in organization on the left, average salary on the right, and it took us about what? It took us about 11 seconds. And we can run exactly the same query now on Ignite. So we can go back to the different notebook, and the only difference in the query would be, let me just clear that output here. The only difference would be is that we have a different prefix here, right? There we have a SQL. Here, since we're basically testing or running against a different data source, we're just saying basically ignite SQL. But query is exactly the same. As you can see, there's absolutely no difference in the query. The same SQL, same group bys. And we run on this query, and did anybody notice running anything? That was how quick it was. So typically, it actually takes 0 seconds, but typically it takes really about 100 milliseconds. So think about the difference again. Let me show you again, because you guys probably didn't catch it. It was too quick. So let me go back to Spark. So let's watch it again. And again, the difference, before I do it, the difference is very simple. Not because we're much smarter, but we do indexes. And in SQL, as you all know, if you don't do indices, if you do full scans like Spark does, you have no performance. There's no way to do anything properly. And we spend a lot of time optimizing our indices, and that's why it works fast. So take a look at this again. This is Spark execution. Watch it carefully. Ta-da. So let's go back to Ignite. Watch it really, really careful, because it goes fast. Done.
What's the data size?
Data size actually is right here. This is the biggest file, right? So it's a 500 organizations, and each organization has 1,000 persons in it. So we're talking about 45 megabyte data set. Very simple data set, but it basically tells you that, again, not a dig against the Spark, but Spark will choke on this data sizes, if you don't do it properly. And it's a very natural thing. It's actually using data frames by now already. But if there's no indices support like in Spark, you do full scan. There's just no magic about it, especially in the complex joins. There is not much optimization you can do in this, and it's essentially what's the difference is. We have a full indices support. There we go. Yes.
But on the first load, Ignite would be as slow as Spark, right?
No, on the first load, we're about 50 times faster.
Okay. You still do the full scan, you need to calculate the indices, so why it's faster?
I don't know why it's faster. We're just faster. It was about you know what? No, I kind of misspoke. It's not 50 times faster. I think it's about 10 times faster. It was about 20 seconds for Spark, and it was like about 800 milliseconds for Ignite. And then Spark dropped to about 11 to 12 seconds, and we dropped to about less than 100 milliseconds. So that's the results. So anyways, again, if you guys, and that's a good example of basically how we, sympathetic or in the same time different, with Spark. Spark is really an analytical system where this kind of delay is not a big deal, right? When you type in something, when a data scientist work with certain kind of interactive systems, it doesn't really matter if it takes 10 seconds or one. It's not a big deal. But in the production systems where you have a kind of OLTP scenario where you have to actually, process something rather fast, as close to real time as possible, these things become a big deal. You cannot have a 10-second delays for anything, especially for a minuscule data sets like 45 megabytes. So that's why, if you guys work with Spark, try to use our SharedRDD because you get all these performances when you run SQL on those SharedRDD, even in Spark. Because the SQL you're going to run on this RDD will actually, will be implemented, will be backed by Ignite implementation. So this is the last thing I have on my slides. If you guys have any questions, I'm more than welcome to answer them. And by the way, if you don't have them right now, we have a booth, literally right on the left side from when you exit. And we're here from GridGain, and we can answer any questions too. The last thing, again, this is the GitHub page for all this demo. If you guys are interested and you want to play with the different things and settings, this is right there. There's a very good instructions how to do it. You guys are going to get the same results if you like it. Thank you. If any questions? Yes?
You mentioned zero deployment.
Yeah.
I'm not sure I understand that. There was a presentation yesterday from Target, blue-green deployments. It's a nightmare for them. Can you comment on that?
Yeah, so the question about...
It's like you're saying, like, we don't have any problem, Ignite doesn't have any problems with deployments. You drop a server application in Siberia, and it's right there. And these guys, like, it takes them 24 hours to...
And they use GridGain or Ignite?
No, we use Hazelcast.
Well, that's the difference, right?
So I don't, look, may have problems, may have different objects, it's a compatibility of new versions and stuff like that. You must have...
Yeah, so we solve more, well, all the jokes aside, we're not going to solve all the problems for you, but we do have the zero deployment that's fairly unique. It's going to solve most of the deployment problems. You don't deploy it. Everything that gets deployed on demand, if you like it. You can still deploy manually, and sometimes for kind of production reasons, or in containers, people like to deploy anything fresh. Fine, we can do that as well. In terms of the, and by the way, this is I say it lightly, but it took us about several years of development, literally several years of development to get this properly done. Anybody working in Java, can you imagine this? Let's imagine you're running a WebLogic on one node. To have exactly the same, to have a class loading from this node to the other node, just to deploy our class, we have to deploy the entire class loading structure from this node to this node. So we have to replicate the entire WebLogic ecosystem on this node just to get the same class resolution on this node. Not only this, we have to constantly version this and maintain the versions across the cluster. That's a big deal. I say it lightly, it looks magically because all of a sudden you type the piece of code here, seconds later it runs in Siberia properly. But it took us a lot to develop this. So it's a nice feature, it's almost invisible to you from a kind of usability standpoint, but it's a big deal from a developer standpoint. Now in terms of the different versions of data, we have very nice a binary object representation that kind of solves the versioning problem. You can add fields to the object. You can remove fields from the object. It's not going to basically break your cache or anything else. So that's what we basically recommend people to use. When your data is changing, schema is changing, we support that natively. There's absolutely no problems with that. So, and we support it everywhere, from a SQL processing, from a data grid, from compute grid, from anywhere. So we're better in this scenario than the competitors. I can almost guarantee it. Any other questions, guys? All right. Thank you. Thanks a lot.